Hey everybody.
No, we're not ready yet.
What?
No. Get inside the machine. It's Test of Ladyada.
Thank you, Machine Phil, for introducing me. Sneaky Machine. Welcome to another Desk of Ladyada. And here at my desk, and we've got the computer behind me. Oh, it'd be really cool if that actually was my wallpaper, just like an Arduino in the background. While Mr. Ladyada is calling this a FUNdaMENTAL Thursdays, it's more of just like a demo. Although this kind of covers a little bit of fundamentals, just like how to make low power electronics. Today is actually a special day because it's Power Monitor Thursday. We're hauling out the old power monitor.
Here it is. Look at this thing.
Power monitor.
You can tell because it says Power Monitor on it.
It says Power Monitor.
It monitors power.
It monitors power.
Yeah.
Okay, we're going to show this off. It's handy. And this is the project I'm going to show off. Here, I'll get that over here so it's nice and clear. And this demo, this project that I wanted to build, I'm basically testing a sample, but while I was testing it, I need to have like a realistic setup so I can measure like the power usage of this power monitor. And so I set up a little demo here. I've got just my Arduino compatible. It's a Metro. Here, I'll lock on it. It's standard 5-volt microcontroller. It's got an Atmega 328P, a USB serial converter. And what I've got it doing is once every 8 seconds, it will do a color swirl of the LEDs for about 1 second and then go to sleep. So, wait a couple seconds and it'll like, go. And then goes to sleep. So just like one swirl of color. And it's just a good demo because it's like, it's visual, you can see it. But this is a stand-in for any kind of project where you want the microcontroller to do something for like 1 second and then stop for like 8 seconds or more. Because that's a common thing. You want to only wake up once an hour, once a minute, maybe like a temperature logger. You don't want to measure the temperature every half second or even like 10 milliseconds. Maybe you only want to measure it once every 5 seconds. And if you're running stuff on battery, it can make a huge, huge difference. So let's check out the code again so I can show what's going on here. So the code is pretty simple. I just start up the serial monitor to help me debug. And then I turn on the LED strip. I make it not so bright so I don't blind myself. And then in the loop, I do rainbow cycle. That's the swirly color effect. It's like a helper function that actually does the NeoPixel color. It's from the NeoPixel test. And then I say, okay, my NeoPixels are done. I'm going to turn them all off. So I turn off every LED like this. And then delay 8,000 means basically stop doing anything for 8,000 milliseconds or 8 seconds. And then I'll say, okay, I'm back awake, time to do another cycle. If you look at the serial monitor for this, let's see if I can pull it up. Yeah, you'll see light up NeoPixel, NeoPixel's done sleeping, and then 8 seconds later, awake, NeoPixel's done sleeping. So it's just this constant cycle. So let's look at the power usage of this project. And here I've got power monitor. Can you go back to the larger screen? Yeah, because it's good to see this. So the power monitor that I got, it's hooked up through USB. So it's basically measuring the USB power. And this little tool is really nice and handy because it can do graphing. It can save the data. It can do different time scale. It can go at the millisecond scale, the microampere scale. Right now I have it to the second scale, so every second is another tick. And then this is milliamps up here. So you can see, for about 8 seconds it's using 60 milliamps, and then it bumps up to 70 milliamps for that 1 second when the LEDs are on. So actually what's interesting is the NeoPixels aren't the majority current drawing element here. The most current being drawn is actually the 60 milliseconds, which we call like a quiescent power. It's the power that's kind of occurring all the time. And then that 70 milliamps here, this 10 milliamp difference, that's the actual LEDs turning on. There's probably a teeny little bit of power that's being used by the microcontroller more when it's actually like pulsing the LEDs, but it's almost nothing. You should consider that 10 milliamps pretty much all NeoPixel. And what's interesting is, I have the NeoPixels powered off of the Arduino, so I'm actually interested, what's the quiescent power of the Arduino versus the NeoPixels? So I actually just unplug the NeoPixels. So if I unplug the NeoPixels, they don't turn on at all, but you see it drops from around 60 milliamps down to 50. So basically we've got 10 milliamps when the LEDs are off. Just the LEDs being off, they draw 1 milliamp apiece. When they're lit, they draw another milliamp on average, and then the Arduino draws 50 when in that delay loop or just doing anything. That's actually quite a bit. So I'll plug in the NeoPixels again, so they'll start blinking. So now we're back to the 60 to 70. And while this is, it's okay if you're plugged into the wall. If you're running off of battery power, this is like horrible. If you're even, let's say you have a battery pack made out of 4 AA batteries, so you get 6 volts, and they're about 3,500 milliamp hours a piece. So 3,500 milliamp hours, and let's just at best say, okay, 60 milliamps. This will run for 60 hours, which is, it's okay, but it's not that long, right? You actually want something that will last a little bit longer than that. You want maybe something that will last about a week. Maybe this is your Burning Man project. You gotta last throughout the entire burn. So let's look at what you can do to maybe make this a little better. Now, you can't really change the quiescent current of the NeoPixels or the light up power. Like once they're lit, they're gonna draw that current. You can't do about this 10 milliamp, but if you can reduce this chunk here, this 60 milliamps, that'll be good. So the first thing I'm gonna do is I'm gonna try using the Sleepy Dog library. So you can actually put the microcontroller to sleep. So this will take the microcontroller, and during that 8 seconds, instead of it like delay, like waiting and waiting and waiting for something to happen, it'll actually like go into a doze mode. Should save a little bit of power. And this is the command. So I'm gonna get rid of this delay.
What's the brand or the name for the power monitor if someone wants to buy one?
It's like Hurricane.
Hurricane power monitor.
Something.
Yeah.
I don't remember.
Is it? Is it really?
It's like Hurricane or Monsoon.
I think it's Monsoon.
Monsoon. There's a little bit of like a naming like dissonance here. The software's called Power Tool. There's like no information.
Monsoon Solutions. Yeah, I found it. I'm gonna post it in the chat.
I'll warn you, they're a little pricey. It's not, if you one day I'll show how to build your own with an Arduino that isn't nearly as powerful, but maybe is good for most uses. But I'll say it's a professional tool for people who use it a lot and are willing to spend money to not have to build their own, which is me.
Empowering tomorrow's solutions today.
That's
Monsoon Solutions Incorporated.
Pretty much.
Yes.
Anyway, so we're back here. So we're going to take out this delay, and then we're going to turn on the watchdog. So the watchdog is a little, you can think of it as like a little electronic dog, and it'll wake you up after 8 seconds or so. So let's have it sleep for 8 seconds and see what happens here. Does that improve our power usage during that sleep or not? No, wait. I selected the wrong board. One moment. Okay, are there any other questions while I'm uploading?
No.
Okay, cool.
It's one of the reasons I like CircuitPython now.
There's a little bit of a delay. It's not too bad though.
Yeah.
Okay. So now it's updated, and yeah, you can actually see there's quite a bit of improvement. Remember, it was 70 milliamps during the LED lit, and then off it was 60. Well, that's down to 45. So we actually just saved 15 milliamps. So let's say now the average is about 45. So previously, our runtime on a couple AA batteries was 58 hours, and now it's, let's see, it's about 45, 78 hours. So we just gained a couple more hours of usage, which is pretty sweet. And we didn't do anything. Like, that was free. It was just software.
Does it spike when it comes out of sleep? That was a question someone had.
Well, you wouldn't notice it because it turns on the LEDs almost instantaneously. So there probably is a teeny bit of like an increase and then turns on the LEDs, but the LEDs again dominate the graph pretty quickly with the amount of current that they require. But remember, while we're at 45, that's okay, but it's not great. Now remember, we have 10 milliamps. That's the quiescent for the LEDs. So if I remove the LEDs again, you'd see it go down to 35. That's the quiescent. But even 35 with the microcontroller in sleep mode, that's not so great. Here you can see the sleep mode. The LEDs aren't actually turning on, so that's the getting out of sleep. But the Arduino actually just has 35 milliamps quiescent. And you're probably like, well, wait a minute. If you look at the datasheet for the AppMega F328, it's going to tell you that the sleep mode is a couple milliamps. Why is it 35? Well, there's actually a lot of circuitry on this Metro. So can you go back to the Metro? So you have to not just include the microcontroller, which maybe has, a sleep current of, I don't know, like 4 or 5 milliamps. But there's also the USB serial converter. It's active. It's doing stuff. That's going to draw another like 5 milliamps. There's an op amp that does the power management. There's LEDs that are lit. There's this 5-volt regulator. This 5-volt regulator is like 20 milliamps, by the way. This is the high current. It's not a 78L5. It's an NCP1117. We can look that up. But the quiescent is not small. Let's see what it says. When they don't mention the quiescent, it's high. That's how you know. You look here when it says like features. If it doesn't mention what the quiescent current is, it's like ridiculous. So you have to like dig to the data sheet because they don't want to. They'd only brag if it was any good. It says here, yeah, like 10 milliamps quiescent current. But when it's regulating, it can be even more. So, it can be. It just adds up. You have 5 milliamps here, 10 milliamps here, whatever. You can quickly add up to this 35 here. That's what it is. It's life. So, doing really low power, battery powered stuff. And we were talking about how, even when you put a microcontroller in sleep mode, you have all these peripherals. Now, if you were really hardcore, you could design your circuitry. For example, you could put a MOSFET to control the LED power here so that you would turn off the LEDs. You wouldn't have to have that quiescent current, and you could pick a really low quiescent current regulator, and you could do a lot of things to tweak it. It is a trade-off to get low current versions of everything. You're going to pay more, maybe even double. It's just like the way it is. Like you want low-cost electronics, you're going to get high current usage. You want lower power electronics, you usually got to pay a lot more. That's usual. Not always, but in general, you're going to pay more for that. So he said, well, he checked out this chip and he's like, hey, there's this chip I found that I really dig. And it's called, can you go to the computer? The TPL5110, Nano Power System Timer for Power Gating. And this is a really interesting chip. And I was like, this is really cool. I like it. It's very simple and easy to use. This is the functional diagram. This is basically how it works. You have your power supply, and then you put this chip and a P-channel MOSFET in between the power supply and your microcontroller. And then you have this resistor, and the resistor tells it how long to sleep for. So depending on this resistor, it can be anywhere from like 1 second to 2 hours. And this will sleep, and then once every 8 seconds or whatever, if you set the resistor, it'll turn the microcontroller off, and it'll keep it on until the microcontroller sends it a signal via the done pin. When it sends a pulse saying, I've completed, it goes back to sleep. This is kind of an external watchdog. Yeah, what's up?
Well, when you're ready for a question.
Yeah.
What makes low current cost more? Is it just more engineering that goes into it?
I think it's a process. A lot of lower cost stuff, you're going to use like transistors, like bipolar transistor logic, and like you just aren't going to trim things as much, and like you just might have more circuitry involved because you're like not as you want to have less yield problems, so maybe you have like more circuitry to take care of stuff. There's just more current draw, maybe like your transistors, if you have MOSFETs, they're bigger, so there's more capacitance, so that's going to take more current to charge and discharge. It's just kind of how it is. For power supplies, it's definitely because they have integrated bipolar transistors, and so they're using a single process, and the transistors are going to draw more power when there's going to be more quiescent current because you have to actually like use that current to turn them on and off. That's kind of my rough view of why.
Okay.
Maybe we'll find maybe a silicon engineer and they'll explain why exactly. But so this is the TPL5110. So it's kind of interesting. It's an external device that you can set up to basically be like your watchdog. Instead of having a software watchdog, you have a hardware watchdog. A little bit more expensive, but it's like theoretically way less power. What's up?
Yeah, that's my signal. So when you're done.
Yeah.
Okay, LiPo versus AA batteries, which is a better option?
Whichever you prefer. It doesn't make any difference. In this case, we just want to reduce the power overall, and then you can figure out the battery that works best, right? If you have the lowest possible power, either battery, you'll be able to get away with a smaller one.
Yeah.
Okay, so we made a breakout for this baby. This is the breakout board, and it has a button. So what you can do is you can have an on-off button that like forces it on. So you have that timer that goes off once every 8-10 seconds or 2 hours or whatever, set with a trim pot. But you also have a button, and whenever you press the button, that will automatically turn on. You can kind of force it on. So that's kind of nice because that way you can have something that wakes up every 5 seconds. But if you want, you press the button, it'll happen instantly.
Does the Arduino have to boot using an external watchdog?
No, you don't have to have a watchdog in an Arduino if you don't want. It's just like if you want to put it into sleep mode, that's what you would use to wake yourself out of sleep. I mean, you could use an external interrupt, but it gets a little dicey. Okay. So, not a lot has to change for us to use this. Basically, we have to set up that pin, the signal pin. So we'll set up done pin to be 12. And then we immediately set the pin to be an output and low. And then, because remember, one of the trade-offs is when we use the watchdog, we wake up right after this. We sleep in this line of code. When we use an external watchdog, it's going to kick us out and going to reset the entire device. We're going to end up in the setup loop. We're going to start from the beginning all over. Okay, so once the NeoPixels are done, instead of having this watchdog, we'll set this pin high, and that's how it knows. Actually, I think you need to have a pulse, so I'm going to put a delay in here. That's it. So now when I hook up the done pin to that TPL, it'll know when it's finished and it'll put it back to sleep. So it's kind of like, hey, wake up, okay, did your job, tell me when you're done, now you're done, put you back to sleep. Okay,
so some more questions?
Yeah, I'm going to, let's go.
Someone knows the possibility to do a Smith trigger, and then the other thing is, don't you need a watchdog? Oh, no, I got it. The other one was a Smith trigger question.
I mean, you could probably make something yourself with an RC timer and a 555, but it's kind of a pain in the ass.
Yeah.
It's kind of nice because it has like that automatically on thing and the signal pin. I mean, you could do this with discrete logic, but like why? I don't know. Not totally my deal. Okay, so this is that breakout board. So I'm going to wire it up. So I will power. So drive. So that goes to 5 volts, and then ground goes to ground. And the trade-off is for us to actually control the power, I'm going to have to use the micro USB cable without the USB serial converter stuff. Like it's going to power straight through here. So when we program it, we'll have to pull it out and plug it into the different cable, but hopefully we'll get it right the first time. And then, Okay, so we have power in coming into VDD, ground is shared, drive is the output, and then done is that signal line that comes from pin 12 to here. And one thing I realized, this is an earlier prototype, you actually need a very light pull down on the done pin because it does jitter a little bit. So in the next version, I put in a 1 mega ohm resistor. For now, I just put it in there just to keep the done pin low. And then I have a little signal LED that lets you know when it's activated. And then this trim pot is what you twist to set the timer. So actually we can, let's turn this, let's disable this for now. And then I'll show you. So if you press this button, oh, I have to power it. Let me, hold on, let me close my serial port. Serial port's closed. Okay, so let me try powering this up through the micro USB this way. Okay, so you see it's lit. And then if I connect the done pin to high, it turns off. And then I can press it to turn it back on. And then when I pulse the done pin high, it goes off again. And then if you wait patiently, very patiently, hopefully it'll turn back on. There you go. So, you know, whatever, 12 seconds later. You can set it with the potentiometer. I just set it to whatever. It turns back on waiting for you to tell it, hey, I'm done. So let's now try this out. We will now wire the microcontroller and the NeoPixel through here. Okay. So it runs, and then I didn't set done. Oh, you know what? I think I forgot to upload the code. Hold on. I have to upload this new code to the micro. Oh, yeah, definitely wasn't uploaded because. And there'll be a final demo. Yay. Refreshing. Okay, so now that that's programmed, now we can try this out. So plug this in. It lights up. And then you can see it turned off because this indicator LED turned off. So let's wait a few more seconds. Turned back on. Did a NeoPixel thing, and then turned back off. And if I want to turn it on immediately, I press the button. It turns on. You see this indicator, and then turns off. So now that we did that, let's look at our power usage. So I'll wait till this automatically turns on. Oh, can you go to the power monitor screen, computer screen?
Oh, the computer screen?
Yeah. Okay, so I'll stop this right now so it doesn't go off the screen. So you see here, there's a little bit of a trade-off. So because we're using this external watchdog, it turns on, and there's this longer delay because this is that bootloader timeout. So because we have a bootloader, the amount of time it's on is twice as long. Like this is the NeoPixel chunk here, and this is the bootloader turning on, blinking 3 times, and then launching the program and then running the program, turning on the LEDs. So, it's like there is a trade-off. The amount of time that we're using power is much wider, because before, remember, we only had this pulse, we didn't have that bootloader pulse. To really get that power usage down, what we would do is program the Arduino to not have a bootloader. We'd program it directly with a USB Teeny or AVR ISP or whatever to get rid of the bootloader so that we didn't have that double bump here from the bootloader and then the LEDs. But the good news is that the amount of current we're drawing is so low it doesn't even appear. So let's put this into microamp mode. And this is the amount of current that we're drawing, about 10 microamps on average. And then once every, 20 milliseconds or 20 seconds, it spikes up really high, turns on the LEDs, and then comes back down. So our average is like way, way lower. So, we do have this large amount of current, but so that's now the dominating amount of power. But let's say, we are turned on, let me put this into milliamp mode. We're turned on for, it looks like 2.5 seconds, and we draw about, 50 milliamps at that time. And that's out of like 10 seconds or so. So 2.5 divided by 10 times 50 milliamps. So it's about 12.5 milliamps on average, because most of the time we're in this ultra deep sleep mode. And then if we have that 3,500 milliamp hour battery divided by 12.5, is now we're running at 280 hours. So we went from being able to run for 58 hours to adding some sleep mode, got us to 77 hours, to now we can run this code for 280 hours straight, because we're not wasting all of that quiescent current when we're not doing anything. So this is a good example. And this is only sleeping for once every 10 seconds. Now you can imagine if you have a low power sensor node, or something that does looks for a command from a remote server, or like a Wi-Fi device or a Bluetooth device that it gets a data command. It might wake up only once an hour or once every half an hour. This can make a huge difference in how long it can last on a battery. So if you did need something that only lasted about 60 hours, you can now use a battery that's only 750 milliamps instead of 3,500. So you just quartered your power budget. Very nice. So that's a demo of why you might want to use an external watchdog timer. Works pretty well. There's trade-offs, right? There's a little bit that slower turn-on time. You get kicked out to set up every time. You need the external breakout. You have to kind of wire up the power, but the savings can be pretty massive. Yeah.
Okay. Can it wake up from an external signal other than the button?
Well, anything that can connect it, that signal pin, there's a signal pin called, I think signal or something, hold on. Delay. Whenever this delay pin connects to ground, it will reset. So for example, if you have it on a PIR sensor, that could be one thing. Or if you had a read relay or something like a door sensor, when you open the door, you would hook that up to that delay pin, and that would cause it to wake up as well. So
Okay.
it's just a switch on there because it's kind of nice to press the button.
Is there a low power RTC that could control the TPL5110 instead of its internal timer for more precision?
Yeah, I mean, you could. It is a little bit of a trade-off. You're not going to. You can either get precision, or you can get low power. If you look at the TPL data sheet, it's not like you get a full. You don't get. It's the amount of time it spends per resistance is exponential. So it's very easy to get it between like 1 and 30 seconds. As you get to like over an hour, it's like chunks of 10 minutes, pretty much. It actually is rather hard to do things that are timing at over an hour with precision. Just because if you think about it, like if you have 5% precision resistors, you're going to get 5% precision at the 1 hour scale, which will be a minute, as opposed to when you're on the second scale, when that 5% will be milliseconds.
Okay. What's the max timeout with the pot that you have? And
It's
then
2 hours. The chip itself can do maximum 2 hours.
Okay. And then when delay is connected to ground, does it reset the board it's connected to, or just connect to power?
When delay is connected to ground, it forces the the drive line high. So as long as if you keep pressing that button, it will never turn off. If you want to go to the overhead, I can show that.
That's not the overhead.
No, close enough.
That one's.
Yeah, that's fine. That's fine. So if I hold this down, see how like the green LED is lit? So I have to let go for it to redo the timeout.
Okay.
So that goes to sleep. So as long as you're holding that button down, it will always keep the drive connection running.
Last question.
Yeah.
Is it temperature sensitive?
Probably a little bit. I mean, there's always going to be a little sensitivity to temperature. I mean, like, again, it's not a precision timer. If you really do want to have a precision timer that like wakes you up once a day, an RTC alarm is better. You can get like a DS3231 temperature compensated crystal RTC and set up an alarm. But like compared to this, it's a lot more expensive. Like that chip is like $3 or $4 a piece, whereas this is like $1, I think.
I think it's the only overhead that doesn't freak out with the LEDs.
Yeah, this is.
By the way.
And there's a couple of variations of this, by the way. There's one that's for enable pins. This one is for like direct power control, but there's one that's like, it's inverted. So it's good for.
So this is a coming soon product?
Yeah, it's coming
Okay.
soon.
When do you want to release it?
I don't know. When is it done?
Mm-hmm.
I don't know. Oh, man, these are pricing. Okay, so it's 30 cents for this. So the breakout will only be a couple bucks. You have to pay for like the PCB, which is much more expensive than the chip and the assembly and the potentiometer. So it's not, I mean, overall, if you want to integrate this into your project, it's probably like 35 cents total, especially if you don't use a potentiometer. Potentiometer is expensive. If you just use a plain 1% resistor, the cost add-on is very little. You have that PASFET, that's like 10 cents, it's like 50 cents total.
Okay.
Not too bad.
All right, so that's it for tonight.
Yay!
All right, thanks everyone. If you like
Glowy.
live electronic programming like this, stop by Adafruit.com, pick up some electronics and more. We're going to keep doing some Just the Ladyada. We have some filming that we're going to be doing this weekend, but I think we could squeeze in some more.
Look, the power monitor, it's $800, people. I gotta pay for this stuff.
Yeah.
It's
And,
really nice. It's worth it. But support
Yeah.
us so that we can afford expensive
it.
test equipment.
Be good to each other, and remember, travel well is better than arriving. It's your thought of the night. Okay. So bye, Ladyada.
Bye, Ladyada.